So welcome everyone to this week's pre-seminar. Today we have the pleasure to have among us Dr. John van der Lindt, who is the Harold Short Endowed Chair Professor in the Department of Civil and Environmental Engineering at Colorado State University. Professor van der Lindt research program focusing on a variety of subjects, although it's centered on performance-based design engineering and testbed applications of building systems for earthquakes, hurricanes, tsunamis, tornadoes, and floods. Professor van der Lindt led both the NIS Wood and NIS Soft project teams between 2005 and 2013, which consisted of 2-story, 4-story, and 6-story shake table tests on the world's largest shake tables. He currently serves as the chair of the ASCE Executive Committee for the Infrastructure Resilience Division, as well as the secretary of the Executive Committee for the Structural Engineering Institute. Professor van der Lindt also serves as the co-director of the Center of Excellence for Risk-Based Community Resilience Planning, headquartered at the Colorado State University, which has been funded by the National Institute of Standards and Technology. His research impact is substantial and includes more than 400 technical articles and reports, and 200 peer-reviewed journal papers. Last but not least, Professor van der Lindt is also the editor-in-chief for the Journal of Structural Engineering. And so today he will talk about the role of buildings in community resilience to natural hazards. So with that being said, I'll leave you the floor, and thank you again for accepting our invitation, John.
All right, well, thank you for the kind introduction. And hearing that, I feels like I'm serving on too many committees now, so. Okay, well, thank you. So today I'm putting together a few subjects today for today's seminar. I'll start with some of the NIS Wood and NIS Soft work, and how the performance of buildings, and then move into community resilience and really talk about some of the work that's been done by the center. So a lot is my work, some is not. I'll try and distinguish that as well as I go along. So I want to start with the stages of resilience, and these may look familiar. Certainly this curve that you see, and hopefully you can see my mouse here. Cursor, the functionality. Obviously, if you're retrofitting or you're actively improving your community, then this could be going up, and then your drop is less substantial during a hazard, whether it's an earthquake or a tornado. And then we look at the within community resilience, we study all of these stages, and that's the immediate damage, which sets the initial conditions, but it sets it for the recovery stages. And those recovery stages become more social and economic, repairing, recovering, things like that. So I want to jump back about, which seems like a fast 8 years, but 8 years ago, to the NIS Soft project, which full title was Seismic Risk Reduction for Soft Story Wood Frame Buildings. And this came about as a result of buildings that were built in the 30s, 40s, 20s, 30s, 40s in the Bay Area, around the San Francisco Bay Area. And locally, they put in place the CAPS, or Community Action Plan for Seismic Safety, and did a study and realized that a large portion of those, about 25% of these buildings, and there's thousands of them, they're 4 stories typically, multifamily rentals, would be very likely to collapse in a magnitude 7.1 earthquake on the Hayward Fault. So we, simultaneously as FEMA P807 was coming out, we put together an NSF proposal and to study other performance-based retrofit techniques beyond these kind of minimal FEMA approaches that were being proposed. So we ultimately, project was, there were 5 different tests, but ultimately we did a large test program at UC San Diego. That's the largest shake table in the US. And here you see this is started with construction, and then ultimately ready for the testing. cross-laminated timber rocking walls with one of the P807 retrofits. And I won't go through these in too much detail. I just want to show you the breadth of the project. The steel special moment frame. This was also what we call minimal level retrofit just at the bottom story. And then steel special moment frames plus wood structural panels. And various damping devices, various viscous damping devices. These were Taylor dampers, and then the frame was built by us. And then we performed collapse testing after pulled out all the retrofits to show. And of course, someone had asked, I sometimes show the collapse testing first, and someone at one point had asked about the order, but obviously we do the collapse test last. And then recycling and disposal. So just to show you the size of these types of tests, here you can see construction going up, prefabricating walls, and remember it's a soft story building, so you can see the opening, the 4 garage fronts and on the bottom floor. And so very soft. There's bracing going in, temporary bracing goes in just for construction, because it's actually somewhat nerve-wracking to be in the building, since it is the shake table itself is in a seismic zone. And so these are on the left, you see these are existing buildings. These are the types that we're trying to model. And then here we see the building. And so you can see, aside from maybe the full plan size, it's quite similar, and that's the idea. So again, as I mentioned, I'm not going to show all the detailed retrofit tests. They were all very successful, but what I do want to show is the collapse test to show you how vulnerable these buildings are. And so to do this, we removed 97% of the instrumentation approximately. So there's 350 centers. We leave 350 sensors. We leave about 10 or 12, a couple of cameras, and those are sacrificial. Now, for those, and I think probably most of you are familiar with earthquake engineering to some degree, in order to select the collapse motion here, just to get into the engineering a little, if you focus on this is MCE level earthquake, spectral acceleration of 1.8 G. And so for an unretrofitted soft story building of 4 stories, there's a period of about 1 second. So you can see how soft it truly is. And so you can see that from an acceleration standpoint, looking at this, there's really no difference in these 3 California motions that were recorded. But one thing I learned back working with Japanese colleagues at eDefense and other things, and I'll show that test in a moment as well, is that acceleration in numerical models, acceleration collapses buildings, but in reality, for a lot of these buildings, it's really displacement. And so it's critical, as many of you know, and many of you model, to get those large deformations into the models. And so at 1 second, so now we're looking at a spectral displacement plot, same 1.8 G. But what you see here is at 1 second, they're all the same. But then the minute it starts to soften and I start to damage this when I shake it, you can see that Superstition Hills climbs right up and triples its spectral displacement. So we selected that motion because we wanted to observe the behavior in collapse and calibrate models. So this is the full, so we've done 4 major tests to this point. This is then we've removed all the retrofits, removed almost all the instrumentation. And so this is the first shake. This is Superstition Hills, and there'll be some, I don't know if you can hear the audio or not, but I'll try and talk over it if you can. Okay, great. So this is, it's a uniaxial shake table. They are upgrading it. This is seismic mass. You'll hear the REU student, he's doing the recording from a lift about 85 feet in the air, I think. And he gets very, even though he helped build the structure, he gets quite happy when it's being damaged. So, and so you can see here, this in the soft story, you can see these towers are here just to protect us. We're we're right behind in a 2-story. We're on the 2nd story of the control room. And so so here we're at about 18% interstory drift, and it's actually bearing on itself in essence. So it's, this would be a building that would need to be demolished. This wouldn't be repairable at this stage. But we did want to model the collapse. So same earthquake again, Superstition Hills 1.8 G, and then keep in mind this little camera right here. This is looking into a room that was furnished. You can't see it from here. And so this was, in essence, this allowed the calibration of a number of models. And so now I mentioned that camera. So now we're looking into that room. You can't see it, but there's a kitchen table and some things in here. And unfortunately, it was a 10 a.m. test, so the sun is directly behind, and we didn't think of that when we planned to put the furniture in. And here you can see people watching from a distance. And so this is that camera that you saw. This is the same shake, but this is the camera that's on that tower. And this shows you just exactly. And so and so this is the result. And of course, here's the various furniture that was put in there. And the idea is really to get. I'll show you in another shake. The idea is to get to get a visual on the accelerations and things from a human perspective. Okay, so now let's if we rewind 4 years to 2009. So what you observed there in Nisoft was a building that's vulnerable. It is not resilient, and it doesn't contribute to the resilience of a community or an urban area. So now, rewinding 4 years, this was a project, the Nieswood project, development of a performance-based seismic design philosophy for mid-rise wood frame construction. And so the idea was to go up to about 6 stories. At the time, we thought 5 or 6. And this is the world's largest shake table. So this is significantly larger. It's about 50 by 65 feet and has a payload capacity of about 2.4 million pounds. This is just the team. I wanted to give a call out to everybody that participated and lived over in Japan for that period. So here we see this is all the wood shipped from the U.S. and Canada, and it's always, I think I've always mentioned this just because of the memory, but the first day you start, it's always raining for some reason on these tests. And so here you see this is a steel special moment frame. Simpson Strong Tie designed this, and it's going to double actually as a lift frame. So we're going to use it as a giant space truss and lock it down, and we're going to lift it onto the table. If the building wasn't so tall, we would be able to use this approach, and you can drive. This is a building mover. They drive it under the buildings outside, and then they bring them in. But in our case, we had to lift it with 2 cranes. And so this is the wood interface. And here you'll see these in a second. These are cages that will capture steel tie-down rods that go up the length of the height of the building. So here's the construction going, another test going there about weekly. So here's so this goes down into the steel moment frame would be under here, and then these are the rods, and this could be like probably a 1 5/8 or a 1 3/4. It looks like, and this goes up, and then the color indicates that this is a very high strength rod. And this is a stud pack, and the stud pack is at the end of a shear wall. So I know it looks almost like more than a stud pack. It almost looks like a solid wood wall. And this is where, I won't be talking a lot about this, but this is where we got the idea of maybe moving to cross-laminated timber for these taller buildings, because that's almost what we're looking at here. And so this is going to take compression and then the rod is going to take all the tension, but it's free to slip down. It bears, but it's free to slip down into the cage so that it doesn't buckle. So here we see maybe 5 stories, and we're getting ready to move it. I think this bridge column test was right before us. So this is the big test day. This was July 14th, 2009. Days somewhat etched. We had about 600 people in the audience that day. And this is the damage inspection team, as well as the project team that you just saw, the 8 or 10 people a couple hours prior to getting ready for testing. Okay, so this is a building that was designed to perform well, and it was designed to have minimal levels of damage in an MC level event. So what you'll see here is this is a triaxial shake. It's 180% of Canoga Park scaled at the spectral acceleration first period. I think it was 0.49 seconds. So it's fairly stiff. You can see the 4-story building from before had a 1 second period. This is a 6-story building with about a half-second period. But this also has a lot of detailing in it with the steel rods. They were designed to control rod elongation, things like that. So it's not just, and then it was done with direct displacement design. And that was an extension of the Priestley work that was developed for back during the press project, but then it was extended into wood as part of Nicewood. So here we see, keep in mind, it's a triaxial shake. You can see some people standing back around, and there's a little bit of lead time here because of the countdown. So now you can see it's triaxial. We get a little bit of accidental torsion in there. And that was really one of the conclusions, is no matter how symmetric everything is, you don't really know that it's symmetric. That was just a minor conclusion, and so you can see, fairly stiff. What you're looking at is on the order at the 5th story of about 3.5% interstory drift. And then this is what we tried to do in the 4 years later in San Diego. And so this is a just a kind of a false floor to give it a look. And then here you can see this is the same shake. This is on the 6th story of the building. And so I always like to tell people, picture yourself having your cup of coffee and your pancakes or whatever you eat, and or a bowl of cereal. That's more my style these days. And so this is MC level shake. And so that's pushing about 2G of 2G acceleration, but it occurs for a very short time. So like some of you probably know, sometimes if the acceleration is not sustained, although you can see some of it certainly sustained, but if it's not sustained, then it may not be as damaging. In this case, it was enough to flip things. So to look at some of the engineering results, here you can see, it's a fairly large building. Here you can see we had a peak force. So this is seismic test. This isn't story. This is seismic test 1, 2, and 3. And so this was more the 72 year, the 475, and then this was our 2500 year MCE level event that you see here. And so this is the X direction, the Y, the X is the long direction. That was the larger component of the ground motion, and that was primarily because the control room about 3 or 4 stories up was on the Y side. It was parallel to the X, and so the general rule at E-Defense is you shake the stronger direction away from the control room, as you can imagine. And so here we got about 1,825 kilonewtons for a peak force and about 211 millimeters of displacement at roof level. And then we were able to, we had 50 optical tracking sensors. So when it was time to test the building, we closed the 6-story doors and for ambient, for sunlight. And then we were tracking with LED sensors, and there were 7 cameras, I believe, tracking this in 3 dimensions. We were able to get everything but one side. We would have needed 9 cameras to do that. So the big takeaway, and this helped us understand more about mid-rise wood frame construction, but there was a number of conclusions and papers and things, like you can imagine, that came out of a test this size. But one of the big things was that we, when we did the 2-story test at the beginning of Nicewood, at 2 to 4 inches of interstory drift, peak interstory drift, we saw this type of damage. And so we saw splitting of sill plates, we saw separation of gypsum wall board, even a ceiling fell, portion of a ceiling, even anchor bolt failure, things like that. Well, at mid-rise, what we noticed, and throughout the entire building, is that you're really at about 3.5% interstory drift. We were getting damage that was more in line with low-rise wood frame construction that was seeing very small drift levels. And the main reason is that the wall stacks, these light frame wood shear wall stacks, they were almost acting like a system themselves. So the wall itself was racking, but then each wall was treating the building almost like and allowing bending deformation and rod elongation and things like that. And so we don't see the same amount of damage that we would see with a more pure or a less more focused shear response when we have combined bending and shear at the global system level. Okay, so I mentioned, want to jump ahead here. I mentioned that with those stud packs, we had the thought of cross-laminated timber. It had been being used in Europe for a number of years. And so a former student of mine, Shaleng Pei, who's at Colorado School of Mines, is the lead on this project, and I serve as a co-PI. And this is a planning project for a few years. And then the Neri Tallwood project was funded in 2016. It was supposed to be finished, but with the ongoing pandemic and the upgrade of the Neri shake table at UC San Diego to 3 degrees of freedom, we were given essentially what amounts to a 2-year extension, really, to test beginning in November. And so the idea is that that'll be a test. You can see the shake table. This is that 25 by 40 foot shake table. It'll be triaxial, and the goal is to test a 10-story post-tension cross-laminated timber rocking wall building. And so these green walls, these are all PT rocking walls, and they let me see if I can. So this is a 2-story. This was a 2-story test that we did in San Diego in 2017, and the idea behind this was to test the concept, make sure that we got all the wrinkles out, and probably spend too much money, because now we're scrambling for that, but but that's par for the course for these large tests. And so here, keep in mind that the shake table, as I show here, the shake table is uniaxial, and so this is a video, a somewhat professional video, actually, that was developed by the UC San Diego Neri site for us as part of that test. And so hopefully it's not too loud here. And so I'll play this. I'll do a little narration as we go, because there's no narration. It's just some nice sound. And so I mentioned it's always raining on the first day, you see. So that's why I said that. It's true. I think if we could not work outside, we'd get away from that. This is that 2-story building I mentioned on the 4-story test. So we're sitting right here in the control room. And then you'll see construction. I think the video is just a couple of, it's about 2.5 minutes. So here we're putting up posts, and we're going to have one floor is going to be just cross-laminated timber, and then one is going to be cross-laminated timber, but we're going to do a light concrete overlay on it. And that's just to get, these buildings, unfortunately, they tend to have a lot of different parts and tests going on within them because they're fairly expensive for one PI. So we have big groups come in. So here you can see this is cross-laminated timber if you're not familiar with it. And so they're laying these big panels. And the building has a very small dimension here because we're shaking this way. And then it's cantilevered out on the sides. Okay, so here's the concrete crew. You can see our rebar, and there should be some sheer. And then the rock walls are going to drop down in here, so that's why there's nothing here. And this is where we're going to put steel transfer plates, and I'll show you those in a second. And the idea of those transfer plates is that they don't transfer any uplift. They're only going to transfer pure shear. Okay, so here's our post tension. That's a half of the wall. They're going to be coupled with right here with, I guess, 5. It looks like you'll see those come in. And then that hole you saw in the middle, that's where there's what we call a steel tongue, is basically going to go in and just transfer shear like this right here. So this is the roof level. This is this second story, I guess. And then they're going to couple right here with the USPs, and that's just taking some of the bending. So you'll see them in a second. They do this basically. And then this is the cage up top where the post tension's gonna come down, and for a structure this size, about 100, I can't remember exactly, 100,000 pounds, something like that, 120,000 pounds maybe. The post tensioning is actually not that significant. We were able to do it with wrenches. We didn't have to, for the 10-story building, that won't be the case. And then there's steel plates throughout. The steel plates are going in to take it up to seismic design mass or weight. Okay, so here is the test. This is essentially Northridge as recorded. So it's I believe it's Canoga Park recorded, and we're doing it twice in a row. And these should be synced. Yes, okay. And so here you can see those USPs that I mentioned, post tensioning, and then of course all the wires and things. And here's that control room I mentioned, and then all of the students working on it, watching and hoping it doesn't fall on us. And so this was the public test, so this wasn't extremely high intensity. It was, I believe it was as recorded, so it was a little bit more than a DBE, but we did run it twice. And I'll jump to the next. So here's a close-up of the rock, and this is just to keep it from trying to walk. In reality, you would, you could have something that looks a little bit nicer. And then, so you'll see again a double view here. And here you can see it rocking. And these were designed, everything was designed as pinned. So essentially the rocking walls are providing pretty much everything. And the idea is that this was resilient and could go through test after test. And in reality, this by the end of this, I believe it went through about 26 shake table tests, including tests in excess of MCE. Without any substantial damage, actually without really any damage. You can see there's a little bit here, you can see a little bit of crushing, and this is maybe, this is quite a few tests in, as you can imagine. Yeah, and so cosmetic damage after, that's right, it was 14 earthquakes for this one, and then we replaced the wall with a different type of system that was proprietary for a different group, or somewhat proprietary, I guess you could say. So the test coming up, it'll be 112 feet tall. You can imagine there's quite we're waiting on the shake table to be upgraded to 3 dimensions. It'll be a 3-dimensional shake, and we're showcasing various mass timber and engineered wood products. And so we expect that to be a resilient structure. So I want to spend just a few minutes now and get into communities. Why do we need these buildings? Well, there's so the national academies had called for a new kind of research, and they said, something that can address the dynamic state of communities, modeling or assessing changes in risk and resilience over time, taking data from disparate programs, bringing it all together, and then linking research and data with decision making. And so the NIST Center of Excellence for Risk-Based Community Planning, which I'm fortunate and lucky enough to be the co-director of, in the first 5 years, we completed this about a little over a year ago, and we were developing an open source computational environment to study community resilience that can ingest these types of building models, and as well as other things that I'll explain. Standardized data ontologies. We didn't get as far with that as certainly we would have hoped, but we have a data workshop coming up in 10 days, I'll mention, and so that's progressing. And then a comprehensive set of test beds and hindcasts. When the second 5 years, we had the renewal about a year ago, we essentially went from knowledge creation to what we call knowledge implementation. In other words, how do we transfer the use of these models into communities so that communities in the US and around the world can become more resilient to natural hazards? So INCORE is the I guess you could say the main product coming out of the center, and it looks at the various components and sectors of the physical infrastructure. It allows the analyst to look at the economic health, social services such as schools and hospitals, and does all this within essentially an information science framework. So we look at different types of hazards. Here you can see buildings is just one component of this. And we look at primarily the key, and you heard me say this early on, looking at the resilience curve. There's social systems, economic systems, and then optimization strategies. How do you take investments that are always limited? There's never enough money, and how do you optimally allocate them to improve your resilience over time? And so we do this in a set of different test beds to different hazards. There's two tiers, I should say, of research tools specifically to the hazard. One is within INCORE, and it can be just a, click, I want a tornado, or click, I want an earthquake at this distance, and it uses attenuation and things like that. Or you can use more complex software, develop it yourself, and then bring it in as a raster file or something like that. And so there's different mechanisms. So we have these 3 thrusts that I just mentioned. I won't go back through them in the interest of time, but 3 thrusts that we look at, and then 6 major tasks. And of course, INCORE is perhaps the largest. We look at the outreach and sustainability. That's intended to be the sustainability of INCORE. How does INCORE go past the years of the center, in other words, so that it can be used? And then mitigation and recovery, which is the optimizations, the economic models, things like that, policy portfolios. Verification and validation doesn't mean anything if it's not checked. I think we all know that. First thing you do is check your answer when you do a structures problem. We do the same thing. It's just really hard to check it at the community level, as you can imagine. So we do try and do hindcasts. And then complex systems, ports, railways, schools, things that, I think, the schools is a great topic right now because it's so complex. What makes people go back, what makes them make certain decisions to go to a school or not go to a school. And those are human interactions. So we use agent-based modeling for that. And then interdependencies, uncertainty modeling, and a colleague that I know some of your professors know, Paulo Gardoni, leads that last task. Community engagement, looking at our Lumberton, North Carolina, our Seaside, Oregon, our Joplin, Missouri testbed, and it engages this, and then to couple it with NIST Community Resilience Planning Guide, and to try and actually take this research development or to implementation. And so we'll have 6 partner communities. Now, these aren't the partner communities, so I should probably have said that on the previous slide, but so these are the test beds and hindcasts. And so what I'm going to present a little bit of today is I'm going to show a little bit of the Joplin hindcast / test bed. So before I do that, one of the major studies that our Lumberton, North Carolina longitudinal field study. It's going to be longitudinal over 8 years. We're in the 4th year. This has been delayed. We're doing this in collaboration with City Hall there. We have a good relationship with them. So the mayor and city manager are helping us distribute the survey, and we're getting some response, but like you can imagine, it's not quite like going door to door. And so the idea was, when this first occurred in wave 1, it's a joint multidisciplinary study. But then it moved into perhaps more social science focused, because it's the recovery and it's not being damaged. One of the key aspects of modeling a community is economic modeling. So we use a spatial dynamic computable general equilibrium model. These are done by a team of economists, not by engineers. I think engineers, we're fortunate enough we can take the class, but there's, I think, there's some finesse to these models, and so excuse me. And so this can measure things like losses in production, wages, changes in the economic sector as a result of a disaster. And then social science modeling, looking at population and employee dislocation, housing restoration and recovery is huge, and business interruption. And so there's tools that do take census data and do synthetic population allocation and things like that. And then, as I mentioned, the interdependency, the uncertainty, and the scalability. We can't model every person, at least not efficiently. And so how do we scale, and how do we do what resolution do we operate out so that we have enough information and don't introduce uncertainty and can make, or at least recommend, an informed decision. Okay, so just I believe this is our last video, I promise. So just want to show. So this is the basics. This is from about 6 months ago. So it's come a little further now. But so InCore operates with PyInCore. It has web services as well as web tools, and then the InCore Lab, which is the many of you are familiar with Jupyter Notebooks, and so we can look at the buildings within, and so this is Joplin, Missouri. We can look at the buildings. We can look at the electrical power poles. So this is every pole, thousands of them. The substations as well. And the graphics aren't great here. I'll show you the real graphics here in a second. And then we can put a synthetic tornado. So that would be that tier 1 tornado, or we can also overlay the actual tornado that hit Joplin, and that would be a tier 2 level analysis where we're bringing in a raster file. And then we can do the damage analysis, and this is just so here we see the level of damage to the buildings showing, and it's at the resolution again. I just mentioned resolution, but it's not great there. And then the substation probability of failure of substations, and of course those with dependencies affect the and so those are coupled to different service areas. Here we see that tier 2 tornado being overlaid. And we'll pull that out, look at damage, and then And then we can couple this with the capital shock stock, which is the computable general equilibrium model, and we can see the change in different household incomes. We can see percent of reduction in employment, and then we can also look at the population dislocation from the tornado. And what you see is, interestingly, the tornadoes here, but what you'll notice is that there's population dislocation due to changes in employment and things like that. Outside of the damage area, and so that's where you start to see these different interdependencies. And so how do we model this? Well, we develop fragilities. Many of you are familiar with, certainly from seismic work. So we would go through. This is actually part of Joplin. We would look at building footprints. And we pull out buildings. So here you see a small house, and actually not that small, I guess, but and then we would map the fragilities. And so we have a portfolio of archetypes that then gets assigned to these. So we're not analyzing the buildings, we're analyzing the archetypes for those buildings. And here you can see it's color coded by archetype. And so this is more the graphics that are in NCORE. This is what you would see, not like you saw earlier. And so here are the buildings related to each substation, 18 substations. And then here we see our levels of damage from Monte Carlo simulation, things like that. So this is the structure of NCORE. This is what we call the conceptual structure. And so what I just showed you is this portion. And so you're seeing, the built environment, the social systems, the economic systems, and then the damage that overlaid the wind hazard, the fragilities, the damage. And then we didn't talk a lot about functionality, but that was embedded in there. And then it passes to the CGE model, which is the economics model, the social science models. And then in essence, and so what I'll show you now is how we step through time, and we can step through and see recovery, and we can then record metrics over time. Things like percent of people that remain in their homes or that can remain in their homes, household and changes in household income, employment rate, earnings by different sector. So these are delay modules, and this is from READY. Many of you are familiar with the READY delay, possibly. I won't go through this in a lot of detail, but this is from extensive data, extensive resource collection, I guess you could say. And so you can see these household incomes. And then this is basically how their repairs are financed. But this becomes a function of that delay. In other words, if your insurance pays immediately, then it's much quicker. And so there's often data missing for anybody that's worked with census data. It's often missing, and so essentially, here you see two pieces missing from a census block. So what we do is we say, okay, this may be missing. So what we're doing is we're going to, we know these 5, and we're going to assume that this one is then the average of those 5. But we do that across this whole block, as you can see, and we would do that for these 2. That's just an example. So looking at this, just to do, a small, I guess, thought experiment, or for lack of a better term. So what we see here is we can see Joplin, we see different buildings. The color scheme's a little different. And then an EF3 tornado. So that's, I think, memory serves, about 160 miles per hour, roughly, for wind speeds. And you can see this is the distribution, blowing it up here. This is the distribution of household incomes across here. And this is from that method that I showed you earlier. And if we do that, then looking at this would be a typical damage run. And so this is insignificant, moderate, extensive, complete. And we would expect, even at an EF3, we would expect at the center of it, pretty much complete damage, or at least level damage state 4. And then here we see our recovery time. And so putting all this together, what we notice is what you can notice is you can say, okay, well, looking at this, what I notice here is that for case one, which is household income one, so these are the people making less than, household income is less than $15,000. What you notice is that you have a number of households that lag in recovery, and so what happens is the scale parameter is significantly larger, and so what that does is, if you look at them here, it's very difficult to tell. They kind of look overlaid. But what happens is these are the people that become homeless, and these are the people that need resources from, for either federal or state or local, things like that. And whereas here we don't see that. We see everybody recovered after a few years. So there's also I think I mentioned in the abstract, I wanted to just mention flood. I'm not going to go into this a lot, but we also work quite a bit with the city, with the Lumberton study. And here we can see some of the flood work. And again, what you see here is that economics and that social science model. And then this shows it maybe a little bit more straightforward than that flow diagram. And we're looking at the state of recovery. So ultimately to model resilience, the buildings are I guess well-performing buildings are a necessary but not sufficient condition for resilience. So they need to perform well, but by themselves, they can't guarantee resilience. They can only contribute, albeit significantly, to that. And so we have to look at the various networks, power network, water network, and I didn't go through all of it, obviously, because it's not a 4-hour seminar, but and transportation network. And then looking at the residential sector, which I showed there, but then also business recovery, which is often a more, it's coupled with residential recovery. It's coupled with many different things, not just damage. And then social institutions like schools and hospitals and things like that. And so just to some closing comments. So community resilience, it's a complex and interdisciplinary endeavor. At least I hope I got the impression across, or the point across, of the interdisciplinarity of this. And it necessitates or requires hazard modeling, modeling of buildings and their interactions, network modeling, modeling of economics, social science modeling, and many of these, we as engineers, we can do much of this, but this part we're not versed in, and so it requires those collaborations with scientists that are specialists in that area. And then ultimately the workflow is required to enable the input and output and the communication of all of these algorithms and the model interaction. But I guess the big takeaway that I want to leave you with is that no single sector has the ability to represent or model community resilience, but each of them is critical in and of itself, and that includes buildings. And so just want to acknowledge NIST for we're in our just starting our 7th year of the 10-year center, and then a bunch of NSF and other contributors to the wood portion of the study, or the presentation, excuse me. And then finally, I just want to bring your attention, this is an open workshop. It's free if anyone is interested, and we'll be presenting. We have NIST is involved. We have FEMA has us. We'll be there presenting. Or when I say there, I guess in their house, but you know what I mean. And then the Sim Center, the NARI Sim Center, as well as Design Safe, talking about computational resources. And then we'll have the University of Michigan presenting their model. And this is the registration. You can just go to the center website. And so with that, thank you.
Thank you very much, John. Wonderful presentation. Does anybody have any questions? I think we have some time.
I have a question.
Yeah, go ahead.
in the first part of the presentation, you were talking about, the shake table tests, and you made the comment about how you guys are doing the 10-story with mass timber and all these things. And so I was curious. So, it seems the NIST Center and a lot of your work is you're focused on the resiliency of the structures and of the cities, which it was a very good presentation, by the way. I thought that was very interesting. But I'm curious because one of the reasons mass timber has sort of become more, talked about, used, well known, is the sustainability aspect. And I'm curious if you've seen any sort of conflict, so to speak, in trying to make not only structures, but the overall city more sustainable versus also trying to make it more resilient. Have you seen that sort of conflict in your work?
Yeah, thanks for the question. So if I'm understanding, you're wondering because presumably to get the buildings to perform better takes more material and more.
Sure.
And so that's kind of the question. And so
yeah, so like for instance, I know that for mass timber, for instance, a lot of the buildings that are going tall, mass timber buildings that are going now are hybrid buildings with concrete. And so when I look at that, I know there's sort of a balance between, because you don't want to over harvest the forest. So to preserve the sustainability of a mass timber building, it's sometimes necessary to include concrete, which is a less sustainable material. So I'm curious if that sort of balance exists from a resilience standpoint, where in order to preserve the resilience, you need to sometimes sacrifice the sustainability, so to speak.
Okay, yeah, and so that's a great comment and question. So I wouldn't say that they're in conflict with one another. I think sometimes the concrete's been used in some of the mass timber buildings and other types of materials, but concrete particularly, and it's really because from a building code standpoint, they had trouble getting approval for the height that they wanted, and that's where the price point was. The demand was there, like I think 18 stories. I think it was 18
in Brock Commons.
In DC, and that was one of the first, and so less was known. No one's tested something that's 10 stories and shown that it's viable, and then there's been fire requirements now. But from a fire standpoint, CLT does great. I mean, it chars and puts itself out, so it's fantastic. So there's really not concerns, but they didn't know all that because NIST and others hadn't done their tests yet, and because that was that's all built and up and people are living, and so I would say that I think you're going to see less hybrid systems. There still will be some. There's some going up in Europe, down in Melbourne, various places, but I think we'll see less and less of that. And I think ultimately, the carbon sequestration and things that come from the mass timber, provides the sustainability. And I think, I'm not a forestry expert, but I think foresters argue that, if they plan correctly, that that they're really not cutting too much forest. And in fact, CLT, one benefit of CLT is it can be just a little bit thicker. It's a little bit weaker, and they use poor quality lumber that they were just going to pull out and put in a landfill anyway. I mean, it's not quite that obvious, but there's arguments for that, and there's all sorts of projects funded to use even beetle kill, here in Colorado, and things like that. And you sound very aware of that. So
yeah, so it sounds like your sort of viewpoint is essentially, as we go and get more data with respect to mass timber, and then I would imagine this might extend broader beyond the structural. It's just a data and experience where you don't have to sacrifice as long as you have good understanding of the systems.
Exactly. Yeah, it's exactly it. And I think one thing that I'd like to see is and I have a project related to that now, but what I would love to see the massive apartment complex that are 3 and 4 story, and if there's some way they could hit the price point with the low quality CLT for that, I think that would be ideal. and definitely don't need additional materials for that.
All right. Thank you.
Yeah, of course.
Thank you, Say. Any other questions, curiosities?
Yeah, I have a couple of questions. First question, given the circumstances, is if have you planned or are you planning on applying those community resilience concept to pandemic-like situations?
So yeah, interesting question. So we are for the Lumberton longitudinal study, we are going to incorporate the economics portion of the pandemic, which is really a large portion of it. We're not doing the health transmission models and things like that, the virus transmission. We have people in the center that work on that, but not as part of the center. There's just other projects that they have, and with NSF or NIH, and and the main reason is, but I think the model could be used for that. I think that's the key, is that somebody could easily, we can, that CGE model that I showed, we can easily take what's called the firms, which are all the companies, and we can just basically sever it. We just shut them down, and it propagates through the whole model. So our economics team is actually doing some work outside of the center. It's a different project for the state of Colorado and a few other states, looking at the effect of, what happens when they open up 25% capacity or 50, and so that they can help inform those decisions, perhaps less from a health standpoint and more from an economic standpoint. So we're partially doing it, I guess, is the answer. Just the economics portion will for calibration, because if we don't, then our hindcasts and our calibrations will be too far off, and so we have to do it.
This is a related question. Is the model also taking into account like social equity, like parameters, like for it?
Yeah, so great question. So yes, from the standpoint of the policy portfolio. So if the policies, if the policy portfolio, looking at that, if you said, okay, we're going to utilize X percentage of this for people in this income or this race, ethnicity, or this, whatever the category, it's a little more complicated, because we're than I'm describing, because of course we're providing essentially risk or resilience informed support, but we can't make somebody make that decision, so while we do want to include governance stability, it's difficult, like we can see just around the US. So we just include certain metrics, things like is the government stable, is it, but ultimately, so we can put them in the model, I guess, is the answer to your question, but it's somewhat manual, but you could put that in as a constraint on your optimization. So you could say, I want this, and it'll come out.
Where I can find the link for the workshop?
Just go to, let's see, Google, here, I'll put it in the chat. Give me just a second here.
Thank you.
Let me pull it up here. Okay. There it is. See, that's one thing that is an advantage, I think, of doing these on Zoom, is I can put something in the chat. So we were talking about that earlier.
Well received. Thank you. Okay, so maybe at this point, I would invite everyone to thank Professor van der Lindt for the presentation. So thank you, it was extremely interesting. And with this, we can close today's brief.
Thank you, John. Thank you very much.
Yeah, absolutely. Thanks for having me, and enjoyed the questions.
Hopefully we'll have you here on campus soon.
It'll be great. Yeah. Thank you.